And that's measuring the pH in the beaker that contains the weak acid that we're starting with, that we need to know the concentration of. So we have several regions of this graph that we can determine information about. So we already have the skills to calculate the initial pH of a weak acid before we add any of our sodium hydroxide. We could do that by using an ice table, as we've discussed before. And then we also have then next a buffer region where we're going to have different concentrations of the weak acid and its conjugate base. And there's a couple of calculations we'll walk through here where we can determine the pH of the buffer solution or the concentrations of the weak acid or the conjugate base as well, or the pKa. Then we have the equivalence point right here where we've added enough of our base to neutralize our weak acid. And we've talked about these calculations already and how to predict the pH of the equivalence point and to calculate what that is actually going to be. And then our last region is here after the equivalence point. And this is when we have hydroxide in excess. So we can also walk through how to calculate the concentration there. And that's a little bit more straightforward with the stoichiometry problem. And so looking at these regions, we can kind of think about what's happening in them. So initially we have just weak acid right here. And in this case, we have, so if I'm comparing the amounts of acid and base, I have lots of weak acid, and that will be in equilibrium with its conjugate base. So there'll be a little bit of base in there as well. My makeshift bar graphs here. Now, as we start adding our sodium hydroxide, we're going to start converting some of that weak acid into its conjugate base. So our weak acid is neutralized to produce water and its conjugate base. And so during this region, we're going to see that acid concentration decrease and our base concentration increase. And so in this buffer region right here, we're going to start seeing closer to equal amounts of our acid and our base in solution. Now, once we hit the equivalence point, that means we've added enough of our sodium hydroxide to convert all of our weak acid into our base, or conjugate base. However, because this is a weak acid and it's forming the conjugate base of a weak acid, some of it will still be in equilibrium with the acid. So even at the, it'll be in equilibrium. There'll be some of the weak acid and the conjugate base in equilibrium with one another. And we'll see that at the equivalence point. Now, once we go past the equivalence point, we keep adding base, then we'll find ourselves in a situation where we have only base around and no acid. And that pH will climb as we add more and more and more hydroxide ions to the solution. So here's a summary of the types of calculations we can do with each of these points on the titration curve. So remember, our curve again looks something like this. And so if we kind of wanted to label this, that initial pH, that's going to be at the beginning of our curve. We can calculate that like a weak acid equilibrium problem. Then when we, if our equivalence point is here, if we're looking in that region before the equivalence point, we can calculate the amount of our acid and our conjugate base and the changes from that using stoichiometry, and calculate the pH using the Henderson-Hasselbalch equation. And so we covered these types of problems when we discussed buffers, how to look at the pH of a buffer as that buffer's composition changes with the addition of a strong acid or strong base to it. And so this is always going to be a stoichiometry problem followed by a Henderson-Hasselbalch equation. Then at the equivalence point, part C, right here, we're going to be able to calculate the pH like a weak base equilibrium problem. So that's different than our initial pH, which was a weak acid. Here we know that all of our acid has been converted into its conjugate base, but that some of that conjugate base will be in equilibrium with the conjugate acid, or sorry, the weak acid, making our pH at equilibrium, or sorry, at the equivalence point, slightly basic in this case. And then any point beyond that, we can calculate the concentration of hydroxide ions that are going to be in excess of the number that were used to neutralize the weak acid. And then we can use that to calculate H3O plus to then calculate pH. So we've already done some of this, a fair amount of it actually. All of the skills that we need to calculate initial pH have been practiced. We've been introduced to the pH before the equivalence point in our lecture on buffers. We've looked at the pH of the equivalence point in our lectures about titration. And we can calculate the pH beyond the equivalence point using what we learned about the autoionization of water and also leaning on our stoichiometry skills that we've developed over the course of this class. So let's put those to use. Here is an example that's going to go through these 4 different regions. And then I'll provide another example for you to practice on your own. So we're going to look at a 25 milliliter sample of 0.05 molar hydrofluoric acid, or weak acid. We're going to use a 0.35 molar sodium hydroxide solution to titrate it. That Ka of hydrofluoric acid that we're going to use is 7.2 times 10 to the negative 4th. Again, this contradicts the Ka that I used earlier in our buffer lecture, as I have found 2 different Kas for this source. In this problem, we're going to go ahead and use the 7.4 or 7.2 times 10 to the negative 4. And we're going to walk through and calculate the initial pH, the pH at the half equivalence point, the pH at the equivalence point, and the pH after the 4 milliliters of sodium hydroxide have been added to the solution completely. And we'll go through these one at a time. All right, so let's start with 1. So here we want to calculate the initial pH. So the information I need for this is what my concentration of weak acid is. I've got a 0.05 molar hydrofluoric acid solution, or it's about 0.05 molar. That's why we're going to do the titration experiment to get the exact concentration with more significant figures. I know I have 25 milliliters, although I don't need to know the specific volume to calculate pH. I just really need that concentration. I also need to know the Ka. And I need to have my acid dissociation reaction. So let's write that out. So we know if we have hydrofluoric acid around and water, we'll form fluoride ions and some H3O plus. And so to solve this, we're going to use an ice table. We're also going to use our pH equation. So let's start with our ice table. We know that initially we have 0.05 molar hydrofluoric acid, and we don't have any fluoride or hydronium ion to begin with. So our reaction is going to proceed towards products to reach equilibrium. So we'll subtract X from our reactants and add it to X to our products. It's 1 to 1 to 1, so we don't need to worry about it being 2X or 3X or anything like that. Our equilibrium concentrations will be 0.05 minus X, X, and X. So looking at our Ka value right now, if I multiply that by 100, it'll be 7.2 times 10 to the negative 2. And if I compare that to my initial concentration of 0.05, which I can rewrite as 5.0 times 10 to the negative 2, I see that these are similar enough that I can't ignore X in my reactant equilibrium concentration. So as I set this up, that means I'll probably be using a quadratic equation. So my Ka is equal to the concentration of my hydronium ion times my fluoride ion divided by my hydrofluoric acid. So 7.2 times 10 to the negative fourth will be equal to x squared divided by 0.05 minus x. I can rearrange this equation so that way it's ready to go into a quadratic solver. X squared plus 7.2 times 10 to the negative fourth x minus 3.6 times 10 to the negative fifth. Now at this point, I'm going to plug it into my quadratic equation, which I'm not going to walk through here since we've had lots of experience with it. And I get that x is going to equal either 0.00565 or negative 0.00637. I'm going to go with this x equals 0.0005 or 0.00565. And that is also going to be equal to my H3O plus concentration, because that H3O plus concentration is just going to be equal to X at equilibrium. So this is going to be 0. All right, so I've completed the ice table. Now I need to work on the pH. So the pH of the solution is going to be equal to the negative log of that H3O plus concentration right here. So I'll plug that in as 0.00565. And when I calculate this, I am going to get a pH of 2.25. And so that's how we'll calculate our initial pH. And this should be familiar by now, working with ice tables and the pH equation. Now let's look at number 2. That's asking us, what is the pH at the half equivalence point? So what is that half equivalence point? So in our titration curve, we have our equivalence point where the number of moles of our base that's been added is equal to the, let's change this so it says moles. The moles of our base that have been added equal the moles of our hydrofluoric acid that we had around. And so that means all of our HF converts into, or is neutralized into F minus. The half equivalence point is when we have equal amounts of our hydrofluoric acid and our fluoride ion, meaning we've added half of the number of moles of our NaOH as moles of hydrofluoric acid that we had around. There we go, that makes more sense. So that means we've got equal amounts of that weak acid and that conjugate base. So at the equivalence point, if we know that these two are equal to one another, the hydrofluoric acid and the fluoride, then that ratio of F minus to HF, if they're equal, has to be 1. So thinking about the Henderson-Hasselbalch equation, that the pH is equal to the pKa plus the log of our fluoride ion divided by the concentration of our hydrofluoric acid, this right here will be 1, and the log of 1 equals 0. So this entire term in the Henderson-Hasselbalch equation becomes 0. That means our pH will be equal to the pKa of hydrofluoric acid. So this will be the HF Ka that we're talking about. So we can calculate by taking the negative log of, and here we're using 7.2 times 10 to the negative 2, I'm sorry, negative 4, will be equal to 3.14. So by the time we hit that half equivalence point, our pH has come from our 2.25, all the way up to 3.14. All right, so now let's review that pH at the equivalence point for number 3. So again, what we're looking at now is that point right here where the moles of NaOH equals the moles of hydrofluoric acid added. So for this one, we're going to need to figure out exactly how many moles we've actually added of our base, so that way we can determine how many moles of hydrofluoric acid were present in our solution to begin with. So we have a little bit of information up here that we're going to have to pull down, primarily that concentration of our hydroxide and the amount that we're adding to it. So let's take this information, there we go, down here. And this problem is designed to do a little bit of predictive work, where we're going to predict the pH of the equivalence point, and we're going to predict about how much of our base we're going to need to add to neutralize it. We can then take that exact amount from when we actually perform the experiment. We can take the exact pH and the exact number of moles that were required of our sodium hydroxide to neutralize our hydrofluoric acid, and then calculate concentration of our acid that'll be far more, will have a lot more significant figures in it than just one. And so here, this is a predictive tool where we're going to use the amount of acid that we're starting with and its expected concentration to determine how much base will be added and what the pH will be. But we can also, from our titration data, we can use titration data, which will be pH values, or when the equivalence point is reached, when we see a change in color in an indicator. That pH value and the number of moles added of our base to determine the number of moles of acid we have. In these cases, we take that known concentration of our base and the volume added to get that number of moles of base. So this is how you would use these types of calculations in lab. Before going into the lab and performing a titration, you would do something that would be predictive, like we're doing here in number 3. So with that disclaimer, let's go ahead and solve this. We know that our concentration of our NaOH is equal to 0.35 molar. And we know that we have 25 milliliters, or 0.025 liters, of our hydrofluoric acid. And that our concentration of hydrofluoric acid is about 0.05 molar. So we're going to use this information to calculate our pH at the equivalence point, along with our Ka of hydrofluoric acid, which is, we're using 7.2 times 10 to the negative 4th. So this is information that I'm going to use from our problem. Okay, so let's remember that when we are adding our sodium hydroxide to our hydrofluoric acid, we're undergoing a neutralization reaction to produce water and fluoride ions. So we are going to now have equal amounts, stoichiometric amounts, of our hydrofluoric acid and sodium hydroxide. So we'll be converting these completely to fluoride ion without any excess at this point. So we're going to try to determine what that concentration of fluoride is. And once we know that, we'll be able to work towards calculating the pH using an ice table. So we have, in this case, to predict how much base we'll be adding, we're going to start with what we know about the acid, which is that we have 0.025 liters of our hydrofluoric acid solution. And we'll multiply that by its concentration to determine the number of moles. So we've got 0.05 moles per liter. That's going to give us a value of 0.00125 moles of our hydrofluoric acid that we started with. And we now know that we have then added, if we do a 1-to-1 mole ratio from our chemical reaction here that has coefficients of 1 in front of our hydrofluoric acid and sodium hydroxide, which are emitted. We have 1 mole of sodium hydroxide for each mole of hydrofluoric acid, because this is a monoprotic acid. And this will be different if it's diprotic or triprotic, so be cautious here. We'll have 0.00125 moles of our NaOH. So if we want to know how much of our base we're going to need to add to get to that equivalence point, we can use that number of moles that we just calculated, the 0.00125, and multiply it by the constant, or the inverse of the concentration. So 1 liter divided by 0.35 moles for our base, which would give us 0.0035 liters, or 3.57 milliliters. So we expect to hit the equivalence point after just adding a little bit over 3 milliliters of our sodium hydroxide to the solution. Okay, but let's focus on the question. We want to find out the pH at the equivalence point. So to find that pH at the equivalence point, we need to know what is our concentration of fluoride ions. Now we know how much of our fluoride ion will be produced, because we know we have 0.00125 moles of hydrofluoric acid and NaOH reacting. And since they will react completely, we're going to form 0.00125 moles of fluoride. And I can do that similar to right here by doing a mole-to-mole conversion, especially if I was looking at a di or triprotic acid. So that'd be 125 moles Okay, so we have our moles component, but now we need to know volume. So our total volume will equal what we started with, which was our 25 milliliters of hydrofluoric acid. And then we have added 3.57 milliliters of our base. Give us 28.57 milliliters total, or 0.02857 liters. So that concentration of fluoride ion at the equivalence point will be equal to our moles divided by our total volume in terms of liters. Oops. All right, that will give us a concentration of 0.0438 molar. All right, so now we have our fluoride ion concentration at the equivalence point. So to determine the actual pH, let's take a look at what that fluoride ion is doing. Since it's the conjugate base of a weak acid, it will react with water in a reversible way to produce hydrofluoric acid and hydroxide ions. So we are going to determine how much of this hydroxide ion we have around in solution And then use that to determine the concentration of our, we'll use that to determine the concentration of our H3O+, which we'll use then to calculate our pH. So let's put in our initial concentrations. We know we have, so this will be an ice table to solve. So our initial fluoride is our 0.0438 molar. And we'll assume we don't have any of our products yet. So our equilibrium, to reach equilibrium, we'll have to form more products and remove some of our reactants. Okay, so now we can start writing our equilibrium expression. So because we're looking at a weak base here, we're looking at Kb. Kb is going to be equal to the hydrofluoric acid times our hydroxide ion, all divided by our fluoride ion. I don't know Kb though. I know Ka. That's been given to me as 7.2 times 10 to the negative fourth. So I can use my Kw equals Ka times Kb expression to solve for my Kb that I need. So that Kb value is going to be equal to my Kw divided by Ka. So this will be 1 times 10 to the negative 14th, all divided by that 7.2 times 10 to the negative 4th, which will give me a value of 1.389 times 10 to the negative 11. All right, so that value can get plugged in right here, and I can plug in my equilibrium concentrations to solve for x. So that 1.389 times 10 to the negative 11th is equal to x squared divided by 0.0438 minus x. I'm going to rearrange this and so I can solve it in terms of the quadratic equation. It's going to be equal to x squared plus 1.389 times 10 to the negative 11x minus 6.083 times 10 to the negative 13. There's that 13. Now, looking at this, my initial concentration is 0.04, and my Kb is 10 to the negative 11th. So if I multiply that by 100, it would still be on the order of 10 to the negative 9th, which is significantly different than 0.04. So this is a situation where it would be okay to ignore x. But because I solved it with the quadratic, I'm going to pass that on to you. But you can check it and see if you get something close enough that you feel good about moving on. I think you will. So when I solve using the quadratic, I get two possible values for x. I get 7.75 times 10 to the negative 7, or I get negative 7.75 times 10 to the negative 7. So I'll go with the positive value. Let's keep that there. And that is going to be equal to my concentration of hydroxide ion and hydrofluoric acid at equilibrium, because that hydroxide ion concentration is x. So from here I could calculate the pOH, but I've been asked about the pH. So I can either, so I've got two routes. I can calculate pOH and then use the equation that pKa equals pOH plus pH, or I can take the route where I use Kw is equal to the concentration of hydroxide ions times hydronium ions to calculate hydronium ion concentration and then calculate pH from that. And either route should get you to the same answer. It's your preference. I'm going to go the second one. So I'm going to set this up. So 1 times 10 to the negative 14th, which is my Kw value, is equal to the hydroxide ion concentration I just calculated, 7.75 times 10 to the negative 7, times my H3O plus concentration, So from here, I'll divide both sides by 7.75 times 10 to the negative 7 and get my H3O plus concentration of 1.29 times 10 to the negative 8. So then I can plug this into my pH equation. It'll be equal to the negative log of that 1.29 times 10 to the negative 8, which will give me a value of 7.89. And this will be my pH at the equivalence point. I can kind of do a little double check here. This is telling me it's slightly basic. And that tracks with my formation of a weak base at the end of my neutralization reaction with sodium hydroxide. That's fantastic. So looking back at where we started, oh, this is a lot. We now have a pH at the equivalence point of 7.89. So now we can look at the pH after 4 milliliters of sodium hydroxide has been added. So let's look at now number 4. So we've added 4 milliliters NaOH. So this is past our equivalence point. Our total volume at that point then in our flask is going to be equal to that 25 milliliters plus our 4 milliliters, which will be 29, or 0.029 liters. And we are going to need to use stoichiometry to determine exactly how much we have left, or it'll be a simple stoichiometry problem. So let's take this 4 milliliters of sodium hydroxide, or this 0.004 liters, and convert it into moles. So remember, our concentration for sodium hydroxide was 0.35 molar. I'll take that 4 milliliters converted into liters, and I will multiply it by my 0.35 moles per liter to get the moles of sodium hydroxide that I have. That's going to give me 0.0014 moles. So at this point, this is the amount that I've added total. I now need to subtract what has been used to neutralize the hydrofluoric acid. So I need to get rid of, or separate out the amount of sodium hydroxide that reacts with hydrofluoric acid. And if I go back to the previous problem that I did some work on this already. I learned that I'm going to take 0.00125 moles of sodium hydroxide to actually neutralize my hydrofluoric acid. So I'm going to subtract that value. So this is the amount that reacts with our hydrofluoric acid, and I have a total added of 0.0014. So my difference there is going to be 0.00015 moles NaOH. So this is the excess that's been added past my equivalence point. And that's going to dictate my actual concentration. Now I have a little bit of hydroxide around as well from my fluoride base dissociation reaction. However, if I have added a lot more hydroxide ion, it'll shift that equilibrium towards the fluoride ion and make that equilibrium reaction have a negligible contribution to my overall hydroxide concentration. So I'm going to use this to moles of sodium hydroxide to calculate my concentration, and then from there determine what my pH is. So remember we had a total volume before of 29 milliliters. So I'm going to take those moles of sodium hydroxide that I have as an excess, divide it by my 0.029 liters of solution, and that'll give me a concentration of 0.00517 molar of my OH minus. So now, again, there's kind of two ways to solve this problem from here. We can use Kw is equal to the hydroxide times the hydronium ion concentration to find H3O plus, and from there calculate pH. Or we can calculate POH, and from there use pKw is equal to POH plus pH to calculate it that way. And either one is fine. I happen to do the first for this in my notes, but it should work fine either way. Actually, I'll do it the opposite way. I did it both ways. So since we did it the Kw way with finding the other concentration of the ion, the first way we'll go this way this time. So I'm going to calculate the POH. That's going to be equal to the negative log of that hydroxide ion concentration, which is the negative log of our 0.00517 molar. And that gives me a POH of 2.286. So my pKw is equal to POH plus pH. So that pKw value is 14. So that's equal to 2.286 plus my pH. So when I subtract that 2.286, my pH is going to be equal to 11.71. And I've added a fair amount of base at this point, so past my equivalence point, so it makes sense that this pH is very high. So that brings us back to the end of our problem. So we'll have 11.71 for our answer to number 4. If you would like a challenge at this point, I'm going to have another practice problem attached to this lecture. But one thing that might be worth trying as extra practice is to look at calculate what the pH is after only 0.5 milliliters of NaOH is added. So this is before the equivalence point. So this will be similar to one of the problems that we did. So take a look at our buffer lecture. And I'll post the solution for this along with the solution for the follow-up practice problems that follow this lecture.